Okay, we're getting started a minute late, and we'll be talking about what's going to happen on Thursday, what homework problems are going to be due, and I didn't bring a pencil with me, so I can't even write down, but I'll take one if somebody's got an extra one, but I don't want to take your pencil. I'm just going to mark on here. I took off in a hurry, and I don't have a pencil on me, and there's none sitting up here. You don't need it?
You don't need to erase. Perfect.
Yeah, okay. My solutions to the homework problems are on these little mini sheets, so not including some Python examples that I'll calculate out. But you've already seen the hints page, which I put up there, and everybody should have gotten the password, right? So that's going to work for the rest of the semester. So I will be, towards the end of class, be talking about what I'm going to do on the quiz, and then what problems I want you to turn in. You won't turn in all the problems, and the quiz will be more selective to you. This is not going to be a crazy quiz or anything. Actually, since I'm talking about it right now, let's just get it over with, so that way I won't have to panic through something. So the problems that I want you to turn in will be 2.3, that's B, D, and I, pretty straightforward stuff. And then I'd like to have you also turn in .6 A and B, and then also the very last problem, kind of the special one, number 6, which is kind of worked out in the Jupyter Notebook for a special case. And then the quiz will be over some sort of energy calculation like you've got going on in problem 5, 2.13. Energy or power, I'll just say. Something that's going to involve having to do an integration of some sort. It might be power, it might be energy, and we'll work through that math today. And then the second quiz problem will be something along the lines of either problem 2.2 or 2.3. Remember I said the quiz would have 2 parts to it. Now here's what's going to happen tonight sometime when I finish putting it together. I will put up the solutions for all the homework problems you're not turning in, okay? And then you know what you are going to turn in, and then you have an idea of the quiz. So after the quiz solutions will go up, and then I'll augment the solutions with, everything will be added then afterwards. It seems complicated, but if I made you the deal of no homeworks to turn in, people would complain, can't we turn in some homework? If I gave you the deal of no quizzes, you'd be always happy, but I can't do that because you got to do some real work, independently. And it also, I think, doing quizzes helps you prepare for the exam. So it gets you focused on that. And I'm grading everything, so I don't know how I'm going to maintain keeping everything going, but that's the way that is. So what do you have to do to prepare for the quiz besides working homeworks and looking at problems? And the quiz will be the first 15 minutes of class. What you need to do is get this printed. So just follow this link, and these are pages that are taken right out of the book, and these will be useful for the entire semester. I could have run these off, but I just didn't get to it, so it'll fit on like 3 pages, I think, is what it is. And right now you only really need what's on the first page if you need a trig identity or something like that, but go ahead and get them all printed so that way you'll have them, and they'll be your crib sheets for taking quizzes, and they'll be used on the first exam. The first exam you'll have this, plus you'll have your own two-sided sheet of notes that I let you use as well.
So is this under course material? Or?
It's under course materials, and I'm going to take you in the back door of that here in a second. But yeah, it's this link that was right down here where it says formulas sheet.
Oh, okay.
But it is in course materials, so that's a link, and you can see the back door into where all the course materials are. They're right in here. And something that I didn't get a chance to put a link to just yet is something that I'm going to talk about. It's called Typora Themes with Page Break _ horizontal bar .zip. And I'll show you what that's about when I look at Typora and how you can produce lecture materials. Chris has used this in the past. I don't know, did I ever give out one of these themes files for Typora?
Not that I recall.
Yeah. I think I mentioned it. I decided I'd give out a themes file. What the deal with the themes file is, I have a particular element in Markdown language that transforms into a page break. Because right now the Typora editor, if you use it at all, and you're going to use it to export out of Jupyter, and then you have another document you can edit in Markdown, and if you want to put a page break between a problem number 1 and a problem number 2, make sure they print on separate pages. This is kind of a handy feature, so you can go print the PDF that you finally send to the printer and have it, put one problem on one page, one on the other, and then when you collate that in with your handwritten solutions, it'll be easier. Am I sounding too complicated? I mean, I do this exact thing because that's how I have to do it, and the Markdown editor doesn't provide for a page break mechanism, but I've modified the files that are in that zip. The files that are in that zip are called CSS files. Does anybody know what that is? Cascading style sheets, something that's used part of HTML. But I didn't write them. They were up on the internet, and then I hacked it is what I did. I found a blog on how to add something to it to put a page break in. Because HTML doesn't have page breaks in it because it's just one continuous scroll, right? So it's just something that I adapted because I'm always looking for the perfect solution that's free, and there is no such, you can get very, very close, and then you have to kind of tweak things in there if you're going to use open source, community type stuff. So that kind of takes care of that for now. So just remember, lecture notes is also a link that takes you directly to that folder that we were just in. And yes, it also takes you to another folder, but that folder I have wired up on my own. It takes you to the solutions folder, but that's only got one hints page in it. I put links out there, but I guess since I'm spending time on this right now, if for some reason or another a video or something doesn't get posted, it might be that I ran in a hurry and I pushed something up from this tablet, which stays in my office, took off to go home or go to a meeting, and then I forgot that I had put it up on the website, but I didn't wire a link to it. So I'd appreciate an email saying you never put a link to this document, but it might be that I just forgot about it, but it's actually on. It might actually be posted, and you'll be able to see by the dates and everything, but I'd still appreciate you letting me know to get it linked up. But if you're in a hurry and you want to get something, it might be that it's actually there and I just didn't link it properly. I know if I used Canvas it'd be a whole lot different, and people say Canvas would be so much better, but I'm just not into that right now. And Canvas is totally private too, right? You can only go into a Canvas site for the class that you're registered for. Isn't that true? So that would solve a lot of my security issues, but that's why I do passwords and stuff like that. But I don't know. From so far being in this class with me, which do you like better? It doesn't matter, maybe. I don't know.
It doesn't matter. Like, because I was like my third class with you, and I'm used to using your
website.
I mean, I'm still terrible at looking at your news column.
Yeah.
But at the same time, like, I know that your stuff is all there, and I don't know.
When you
And plus,
you have.
you're
Yeah.
very responsive. So
Well, I wasn't over the weekend, but I had my plate kind of full. But at any rate,
the weekend.
Canvas you have to log into though every time, don't you? That you want to go into it? Doesn't it have?
Google Chrome now and log in.
Okay.
Yeah, me too. Microsoft likes
It's
my
up to you.
face.
Well, I'm not going to change. I'm not going to change. The reason why I do it though is it's like I can tell people in the community or anybody, I'll say, go look here, and it's totally available. And the university, it's publicity in a sense. I mean, it draws a lot of comments. I get somebody every week that says, I want your lecture notes, and not all my notes are unlocked. I mean, I get them literally from all over the world, and they're always telling me why they need access to stuff that I don't want them to have access to.
Tell them to take the class. They can do it on
Well, I know, and that's what I've done. That's what I do. So, but it also provides some sort of a, it provides some breadth to what we're doing in the program. So, at any rate, we left off, I think, just barely getting started in this chapter, and
We hadn't touched any arithmetic yet.
yeah, we hadn't touched any math yet. So, but I've been doing time with students in my office since Thursday. So, signal models for this class are very deterministic. In other words, completely specified functions of time. Remember, I put this up, I think, I scribbled this on top of the chapter 1 intro note saying that when we get into modulation theory, which will formally start in chapter 3, we have this basic scenario. We could have the amplitude of the cosine wave be a function of time. We could make the frequency be a function of time, and we could make the phase be a function of time. But this is an example of a deterministic function because everything is completely specified as a function of time. When COM2 is taught, it makes extensive use of random signals. So in a random signal case, you've got a function of time, but you've also got an attribute of the signal that is random. So like a random variable. And random variables are a ways down the line for those of you taking prop and stats right now, where you talk about something being a random variable. So we could have a digital COM waveform or an analog waveform that's got some characterization in terms of probabilistic ideas. We will use certain types of waveforms in here, and they're very easy to generate in Python because Python has a lot of random number generator functions. Actually, there's a whole package within SciPy called scipy.stats, which is just phenomenal in what it can do, but NumPy has a lot of basic stats things in it too, which I think you're looking at. Those of you taking prop and stats right now, you're going to be doing some of the basics, but we'll use them in here too. Like if you want to find the power in a periodic signal, you can find the variance of that signal, and that will find the power if you scale the axes accordingly and things of that sort. And of course, mean is there, standard deviation, and then there's random dot something, which gives you all the random number generators that are out there. I think Dr. Semiari said he's already shown you some of that. Is that true? Something under random? Those of you in prop and stats right now. This is the first time in my time of using Python that I can actually say there's another professor that's using Python in our department to teach signals and systems related concepts. So I'm really happy. Previous young faculty member we had was totally locked on to MATLAB and was like he was never going to give it up. And I just can't believe that a young faculty member would be that stubbornly addicted to using an expensive commercial package. So I'm really happy that we have somebody that's interested in doing that. So we will see some random processes along the way, but not formally defined. There's a section in the book. This book has a whole chapter on random processes. This book has a miniature chapter on probability and random variables too. So that's in this book. The next type of classification is whether a signal is periodic or aperiodic. So that's not the only way of dividing up signals, though. So far we've said signals could be deterministic or random. Another way of looking at them is periodic and aperiodic. And then another way is going to be power signal or energy signal. Periodic signals tend to be power signals, and aperiodic signals tend to be energy signals. That's kind of the rule of thumb, but there's some variances on that. So signal is periodic if it has this property that you can pick up the whole waveform and move it over any multiples of some period t naught, and it just keeps, repeating itself. And t naught is generally the largest value that this works for. So if the signal had a period of 2 seconds, you could pick it up by 2 seconds and move it over. You could move it over by 4 seconds and it would do the same thing, but it's called the fundamental period, and that's the homework problem the second homework problem that you're turning in. And then the definition, as the book defines it, a signal is aperiodic otherwise. So if it's not periodic, it must be aperiodic. So really common examples of periodic signals are sinusoids, assuming that they've been running from minus to plus infinity. Aperiodic signals are individual pulses or some unique signature type waveform. I guess something that always comes to mind for me of an aperiodic signal, and this was on the news, that I got an alert that there was an earthquake that occurred down in the ocean, in the Gulf. Let's see, Cuba and what other country is it near? It's Jamaica. It's a 7.7 earthquake, so pretty large one. But a seismic event like that is definitely a good example of aperiodic, because it comes up strong and then it's gone again.
It's the aftershocks that get you.
Yeah, and those would be aperiodic signals, either taken as a whole or taken as an individual event. Really what it comes down to is how do we look at things. A sinusoid is, if we generate it in the lab, it's going to have a starting point and an ending point, because in time started and time ends, but we don't, we can't really draw a line on when time is ending, but we have to be realistic in our engineering and just say it somewhat comes down to a point of view. So if we say a signal is periodic, it's up and running for a very long time, and we're looking at it that close. The waveform is, has an extent that makes it look, for all practical purposes, as if it's periodic. So this also is the first special type of waveform to define, and this is the book's definition of the rect function or the pi function. So capital Pi is this function that runs, it's active or on with a unit value from minus 1/2 to plus 1/2. Typically, though, we end up scaling this function, so a tau gets put in the bottom, and then a tau goes in here, and then this becomes minus tau over 2 to plus tau over 2. And if you ever get confused about why that is, all you have to do is take the argument of the function, which we've now modified by scaling, and say we're interested in what interval is t over tau running from minus 1/2 up to plus 1/2, and then all you have to do is multiply both sides of the equation by tau, and then you get the minus tau over 2 plus tau over 2 and so on. You've seen these ideas before though, right? Like in 2610 and so on. The other big function though that Dr. Zeemer uses is the capital lambda function, and I'll just put the tau in here right away. This function is that as long as magnitude of t is less than or equal to tau, and it's 0 otherwise. So it's a function whose shape is a triangle that runs from minus tau to plus tau. on the time axes. And both of these are defined in the Python library that I've created. It's in the SIGSYS module, which I alias to SS for SIGSYS shorthand. And then there's a function called rect. So in the Python library, I call this rect, and then I call this one try. And they take two arguments. The first argument is the time axis, and the second argument is that denominator parameter of tau. So the tricky thing to remember about these two aperiodic signals is the full width of the rect function is exactly tau, and the full width of the try function is 2 times tau. And that's just the way it's defined. And the reason why the try gets defined that way is if you convolve a rect with a rect, or pulse function, you get a triangle function of twice the width, because convolution always stretches things out, right? So if you have a width tau pulse convolved with a width tau pulse, it'll become a 2 tau width base, and it's triangular. We'll be reviewing through convolution a little bit later, but that's the reason why it is that way. And we'll be looking at these two waveforms, and then we'll Fourier transform them. The rect transforms to a sinc function, as we'll learn about and review, and the try transforms to a sinc squared function. And that's as a result of the convolution theorem in Fourier transforms, which says convolving in time domain is multiplication in frequency domain. But we'll be going through that again. These are all core things, though, that are really important. And then we'll also have the rect function and the try function can be defined in the frequency domain, too. And then we'll have the dual of that, the inverse transform, in the time domain. So we can have band-limited frequency domain functions for modeling. So this picture down here just shows a periodic cosine wave under the assumption that it starts at -infinity and goes to +infinity, the rect function, and then a noise signal, a random signal. Quick review here. Phasor signals are talked about in the book. You've seen them before. Whether or not I put the tilde over it is not something that I focus on too much. I might just write it as x of t, just saying it's a complex sinusoid. The tilde notation goes back to perhaps in Signals and Systems or 3205. Is everybody okay with that idea if I don't put the tilde part on there? It is going to come up later in the class, though, when we talk about analytic signals in the Hilbert transform. But a lot of times things are gotten from context. And that's one of the things about me just writing x of t. Is that going to be a periodic signal, an aperiodic signal, a random signal, a power signal, an energy signal? I mean, that's part of what you have to be able to do is look at it and see what is it once you have it. I remember when I wrote the Signals and Systems for Dummies book, the editor that I had got really confused about signal classifications, and she was trying to be really smart, like an engineer would want to be smart, and she was tried to understand it all, and then the next thing I did was get her confused. It's like, this doesn't make any sense. You have this, and then you have this. I said, yeah, that's the way it is. We have these different classifications. You can't put everything into a simple A, B, C, and D kind of a thing. There's different ways to classify. And you guys have been broken in already, so it's not too confusing, right? The fact that you can classify things differently. That was my initial really bad experience with my editor, though, because I know she was trying to make it easy. And
Well, it was for dummies.
yeah, and one of the principles of writing a dummies book, which I had to get beat into me over and over again, is you have to be able to show the steps to go from the start to the end. So if it was a little problem that had a little bit to it, you have to show them the steps. And that's one of their founding principles, step by step. Let me write that out. So I had to be reminded of that time and time again. So this is, the more formal idea of the phasor signal. The real part would be x of t. And then we can use Euler's identity to break that complex sinusoid into cosine plus j sine. And we can have the magnitude and phase representation, or we can have the two complex sinusoids if you break it down in the opposite direction from Euler's identity. And so that would be this idea right here. So most of the time I'm more interested in just, this is kind of where it's at, just going from the top to the bottom and back up again. The intermediate step is not that relevant to write it all out. But then that gives rise to how we can plot line spectra of signals on paper. For periodic signals, you can say, okay, the line spectra of a signal will decompose it spectrally into an amplitude and phase spectra, and we can either do a single-sided or a double-sided. Most of the time, mathematically, the most useful one is to do the two-sided, because then you're getting the full representation. If it should happen to be complex, you'll get just a single spike. You won't have a negative frequency or a positive, because you'll only have a complex sinusoid that's spinning clockwise, so that'd be a negative frequency, or counterclockwise is the positive frequency. But in the lab, when you're working with a spectrum analyzer, this is what the spectrum analyzer shows you. It does not show you the negative frequencies. And when you're looking at the spectrum, like the FCC chart that we were looking at last week, that's only positive frequencies. So it's possible to get kind of hung up on why the negative frequencies, but that's the mathematical completeness that we need to have. And in software-defined radio, the spectrum is unique in positive and negative sides because we do have complex signals. If we're only dealing with real signals, then we always have that symmetrical character, right? A real cosine has a spike at positive and negative, and then the phases will be equal and opposite between the positive and negative. This idea right here is what is dealt with in the very first problem. So the very first problem gives you a spectral picture, then it says, okay, we're supposed to be able to go back to this from the plot, or vice versa, go from the waveform to the two-sided line spectra. And then if the problem was to ask for the one-sided line spectra, then you would just show the positive frequencies, and then you have to remember to double this so that it's A rather than A over 2. This is also this is very much related to that first homework problem too, so I guess I won't go through it. But if you want to get the line spectra, formally you could break everything down into complex sinusoids, and then you can plot the picture, and then you could take the picture and go back again. So however you want to do it. You've seen this before though, and if everybody's good with it, I'm just going to keep pressing on because there's definitely lots more to go. This will help us in Fourier series though when we get to that a little bit later. Okay, along the way we're going to stop and look at singularity functions, and the really most important singularity functions we have are the delta function and the step function. So the unit impulse function or delta function is the mysterious signal that has zero width and area equal to 1. So it appears that it's going to infinity, but only in the limit as we model it with a test function. But it has the operational behavior known as the sifting property. So the sifting property idea is that if we're putting in the integrand and we're integrating it a waveform times a delta of t minus t naught, it will sift out the functional value at t is equal to t naught. And as long as the function is regular, it doesn't have discontinuities and things, we can say things like that. And that's the characteristics unless we have some bizarre thing happening. Like if you integrated and you put in a delta function at t minus t times x of t dt, the fact that the integral is stopping at plus t kind of gives you a worry that if this is the waveform, then we're putting a delta function, effectively a test function, as I'm showing it here, that because we're going to stop integrating right at t, we have to wonder, are we going to just take half of that value? But that's just kind of an ill-posed problem. Generally, it's either in or out is generally the way we'd look at it. Either the delta function has been entirely captured by the integral or it's not. But if you really want to split hairs, you could say it's half, and we're not going to bump into that really ever. But that would be a concern, right? And in prob and stats, delta functions are used when you get up into random variables, and they're used in a more less ideal fashion too, where you don't worry about the end conditions. There's various properties of delta functions. In one of the homework problems, let's see,
2.6.
yeah, which you're going to turn in, you do have a case like I just talked about with the ends, but he carefully sets the problem up so it goes from 10 plus and minus 10 minus, so you don't have to split hairs. But then you also have, in the problem before that, you have a case like this. So you have to deal with the delta function by normalizing it by the magnitude of a. Or if you choose not to do that, you could always use basic calculus and change of variables if you wanted to remember it that way. Does everybody remember changing variables in an integral and things of that sort? So if you were integrating if you're bothered by what to do with that a times t in the argument of the delta function, you could let lambda equals a times t as a substitution in the integral, and then you could do the differential, say d lambda is a times dt, and then you could come down here and say, okay, the limits are not going to be changed by letting lambda equals at, because a is going to be finite. And then you could come along here, and I'm assuming this example a is positive just for convenience, but when you rearrange this, then you'd make the substitution delta of lambda, and then dt gets replaced by d lambda over a. And what the book is pointing out, that it actually has to be an absolute value, but see how that would work out? I mean, calculus would let you see how that scale change works out by just doing a change of variables, because now you've got the integral of just the delta lambda and not with a scale factor in there. But it works its way out using basic calculus. That's good, right? Why did you learn calculus? You learned it so you could use it. And you don't use it all the time. I don't use it all the time either, but I use it often enough that my skill level stays fairly good. I don't remember all the integration formulas. I have a handbook that has integral formulas in it if I need it, and I refer to that. Or I guess there's a website that takes care of that, or I might use Mathematica or SymPy or something like that. Okay, this special case of the sifting property number 3 is one we were just talking about on the boundary, that's on the boundary conditions. And then there's the sampling property, which just interchanges things, because if you multiply anything times a delta function, you're really saying you're just locating the amplitude of that function at the location of that delta function. So when you go to plot this thing, you'd say there's just a delta function, and the height of the delta function is going to be x at t naught. And we'll utilize this when we talk about sampling theory later, but that's kind of an application of it in sampling theory. And the other thing about delta functions is when you draw them just with the arrowhead on top, you're just implicitly saying the height of the delta function involves just representing the area of the delta function, which is always 1 by definition. Derivative property, I'm not going to be using it here, so I could say no worries. It's just in the notes and it's in the book, but it's an interesting thing to consider it, especially if you want to look at what's going on with it. There's also the test functions for modeling a delta function. They're sometimes useful in solving some types of problems, but I'm really interested in the operational properties of the delta function, and this can be useful, but it's kind of taking things a little bit over the top in most all cases. So I'm not expecting you to be able to work with the test functions unless you need to prove something to yourself, and we can certainly do that again in the package. I mean, I put that inside of the SIG-sys module here when that gets imported in Python. I do have, oops, I'm trying to put a cell down below, and when I'm running a video recorder, a lot of times it doesn't work, but ss dot. I guess I have to run this because I had my system shut down. So I have this function delta epsilon, and the delta epsilon function, if I do shift tab, I'll get the help on it. It lets you create an approximate delta function that has area 1 but has pulse width epsilon. So you can play around with a test function type delta function if you want to numerically. And that's what this example was here. As far as I'm concerned, anything that you can do numerically and you think you need to do something like that to understand something better, that's what tools are for. Math is math, and then if you want to understand it better, just create a little example numerically to try to get your feet on the ground with something that may be confusing to you. The unit step function is defined as the integral of the impulse function as you bring the integration limits up from -infinity to t is the standard way of doing it. So as you integrate through the delta function, you'll start at less than 0 and you'll start integrating, and then when you get an epsilon past 0, you will have integrated the whole delta function and you'll have 1. At t is equal to 0 in our book, it's not defined, but your brain looks at that and says, well, if it is this little test function sitting there and I integrate halfway through it, I should have half the area, right, if it's symmetrical, and then it rises up. So it's just the step function and delta function are both tools to help describe things mathematically. The reality is what systems really do. And when you take circuit theory, you definitely understand that you can't have a 0 rise time in a circuit. You cannot actually have a step instantaneously go from 0 to 1 because there's always going to be some distributed capacitance and inductance in the actual circuit which will slow it down. Inductors always have series loss. Capacitors have dielectric loss as well. That's hopefully in your mind because you've used as a foundation to get to this point, you've used physics and math. So which do you like better, or do you like them both? I like them both, but which do you tend to gravitate towards, physics or math? Because that's the basis of electrical engineering, is both backgrounds.
Probably physics because it's more fun.
Okay, and it's real, right? Physics is taking it. Physics has pure theoretical, but it's more hands-on oriented. Math, though, is a convenient way of abstracting things and just having a pure math description, and then the delta functions and the unit step functions are what we engineers and physicists like to include to kind of idealize the description of things. And we know how to deal with it. We're practical about it. We say we're not going to get all bent out of shape in our brains about the math is so hard, and mathematicians don't like delta functions because they're so delicate to handle, but we have the operational math ideas that we use in engineering with the delta functions and the step function, and we just are okay with it. We're looking for something practical. We're not looking to drive the math to the limit. So, and I'm very good with that too. So now other signal classification means, so we're jumping off into another classification means is energy or power. So the instantaneous power is voltage times current in a circuit, and it could be written as I squared times R, V squared over R, etc. And in signals and systems theory, we tend to keep the resistance R suppressed in the model, and we'll say it's a 1 ohm system. So unless told otherwise, everything is in a 1 ohm system. So squaring a signal gives us the ability to have the instantaneous power, and then if we integrate it, we have the ability to get the joules of energy that's in that signal that's being represented across a 1 ohm resistor. And that's just an abstraction that's kind of a convention. When you get into real things, like in the communications lab, then you have to take into account the resistance environment or the impedance environment. And all the measurements done with the COM test equipment is in a 50 ohm impedance environment. So then the reality hits home that you have to include 50 ohms in that calculation. And you do that stuff in the COM lab experiments where you actually get the impedance level involved. And I will throw that at you every now and then too, because I believe if you always think of things in 1 ohm and then all of a sudden somebody says it's in a 50 ohm environment, it's like panic. You know, I'm not used to that, so take you back to that. But unless told otherwise, assume it's 1 ohm environment, so we can get power in watts. So I'll expect units when you work problems and do calculations. So like if I said there'd be a calculation for power or energy, so I'm expecting when you do the quiz, you will put J for joules or W for watts. I'm looking for units on there. And you can get that by just being given a signal, and if you square it and average the waveform, you'll get the power. If you square it and just integrate it, you get the energy, or actually you do either of these two equations to get energy or power. And as I said last time, this circled equation for power is very fundamental. The fact that we don't have to take the limit to get the power. We typically are dealing with periodic power signals, so we just have to integrate over one period. So to get the energy, you generally think of that formula, magnitude squared and integrated, to get the energy in joules, and then recognizing what the period is, then you can integrate over one period, which is effectively finding the energy in one period, and then you have joules per second, which would be watts, right? Is everybody good by that? I can't emphasize enough, because I think early in signals and systems, these definitions involving the limits are problematic. The energy one is not too bad, because you can quickly take the limit as t goes to infinity in the integral and just write the limit as minus to plus infinity. But then the nastier one is this one right here. How do you how do you get that to work if the waveform is not periodic, or you don't know what the period is? And so how can you actually integrate it? Test equipment does do this, though. This is what goes on with the spectrum analyzer that you've been playing with in the lab. You plug a waveform into it, and it's calibrated. The way the spectrum analyzer is calibrated to display the spectral line heights is as a single-sided spectrum, assuming it's in a 50 ohm environment, so it's going to display it to you in decibels relative to 1 milliwatt. So it just has that pre-built into it. If it's not a sinusoidal type waveform, then the calibration is not going to be quite what you expect, and won't really run into that, because in lab 2 you'll be using signals that decompose into Fourier series expansion, and the spectral lines will always be still in dBm, which is related to, say, the power that's in the periodic pulse train, but then it gets distributed in the frequency domain over spectral lines with so many dBm per spectral line. So the definitions and how you classify is energy if and only if the energy is bounded such that the power goes to 0, which would be kind of of necessity here in this red circled equation. If the energy is finite, then you divide by T naught. If it was the first definition there in the limit, then it would go off to 0. Didn't say that right. If the energy is finite, then the power would go to 0, because you would not be able to use the red circle equation. You'd be using the full limiting case, but you'd only have one piece of waveform, but you'd be averaging over infinite time, and then that would drive that to 0. And if it's a power signal, if and only if the power is bounded, which of necessity implies that the energy goes to infinity. This is kind of a standard example with a unit step function applied to a decaying exponential. So you can get the energy in the exponential. And if you let alpha, the decay constant, set equal to 0, then it just becomes a step function, and then you find out that the magnitude squared of that is infinite because the area is infinite. So now we've just jumped from it being it's no longer an energy signal. And then we can calculate the power for that signal by using the limiting equation in this particular case, because it's not periodic, and the power ends up being equal to 0 in that case. I've got this right. Oh, it's equal to 0 for alpha greater than 0. For alpha equals 0, we get a squared over 2, which, that makes sense, doesn't it? If you have a DC source that's producing a voltage across 1 ohm of A volts, the DC power from that would be A squared, right? Just V squared times I, but just assume it's 1 ohm, so V squared over R of 1 would be V squared would be the power. But if it's turns on at T is equal to 0, considering the entire timeline from minus to plus infinity, you're only going to get half of that power because it's only on for half the time. So that's how I always remember that. Does that sound good? You have to use some common sense in there too. And in this case, if alpha is less than 0, then it exponentially is growing, and then the power goes off to infinity. Now, this is a good discussion to have very briefly. Does it make sense to have some signal that has infinite power? There's no practical scenario. My wife and my son were watching the Chernobyl miniseries that I guess was on a few years back about the nuclear accident, and
Last year.
it was just last year. Well, they were just watching it because they can dial back in time and watch it. But maybe a nuclear reactor comes close to that, but it's still finite energy. If we're looking for a source of energy to supply all our needs, the sun has got what appears to be a near infinite amount, but there's no practical signal that we can generate as on Earth with our hands that's infinite. So it's just a concept, right? We would like it. That's sort of like something everybody would like to discover in their backyard, a source of infinite energy so they could power everything. I don't know. It's intriguing to think about that. But this is the mathematics, right? Math models can do anything outside of the physics, the reality of things. So I think that's what makes engineering so much fun, is we can dream with math and then we can control our dreams with physics and say, it's cool in math, but guess what? We can't do that. Does anybody else see that as what makes engineering have an interesting twist? We're not just thinking so abstractly that there's nothing practical. So this is the example in finding the power in a sinusoid, and this will come up over and over again. So the energy in a sinusoid is infinite because the magnitude squared gives us cosine squared, which is non-negative, so it has infinite area as we take that limit. But then if we look at it as being a periodic signal, we can just find the power over one period by taking the signal squared and dividing by that period. And here I just sort of proved the result for periodic signals. I can take the limit, but I discretized it into periodic chunks and get a squared over 2. Trying to think. An extension of this would be if, and I think this comes up a little bit later, remember what the power is if you sum two sinusoids, and I'm going to assume that f1 does not equal f2. What is the power for the sum of two sinusoids not of the same frequency? Intuitively, what would it be? I mean, I can spend pages talking about this, and maybe I do at some point, but it's going to be a1 squared over 2 plus a2 squared over 2 is what it works out to be. When you take and square x of t, you get a cosine at f1 times a cosine at f2, but then you think about plugging those two cosines inside the integral, where you're integrating the thing squared. And because those two cosines have already been squared, that cross term, it contains a cosine that's at a frequency of f1 plus f2 and f1 minus f2. And because f1 doesn't equal f2, those cosines in the cross terms are not going to, they're going to integrate to 0 because their average value will be 0. So you end up with just the square of the two individual terms, which is what I wrote down there. The cross terms go away.
Yeah, in your notebook it is the same problem.
I think I put that in there kind of to prove it in numerically too.
Yeah, but I don't see when f1 is equals to f2, it's not this. It doesn't come out to be a1 squared over.
That's correct. Then you have to revert back to a formula that you learned about in 2610 called the phasor addition formula. Remember that?
Yeah, but why don't you just apply that to the square of this thing? I mean, what's keeping you from doing that?
In which case? This case or a different case?
Same case, this case, yeah.
Where f1 equals f2?
Yeah, you squared this equation right?
Yeah, well then what you have to do is you have to just add the waveforms together, taking into account the phase, and that's what the phasor addition formula was all about, right? In this case, it would just be a1 plus a2, because they would add together perfectly because they're both at 0 phase, but if they're at different phases, then you use the so-called phasor addition formula.
Yeah, I'm just saying why What's keeping us from using, this X,
X1,
1T plus, like phi 1 and phi 2, right? Anyway, okay, you might take too much time right now.
yeah. I'm not trying to confuse you, I'm just trying to make you think on something that it's kind of important, because you don't want to stumble over the fundamentals, and this is something that once you get over it, you don't think about it anymore. You just hold on to it and you keep using it because you've proven it once, but it's not. Some things are longer, take more time to prove. But once you have them proven, then you don't have to go back and wonder about it and worry about it anymore. Isn't that also true? I mean, you're good to go, and when you get into trouble, you just sort of say, maybe not clenching your fist, but you're just sort of saying, I know this is true, and I can now use this confidently. And in prob and stats, you have random processes that you would get into, not in the 3610 class, but if you have random processes that add together and they're uncorrelated from one another, then the cross terms go to 0, and that builds up from random variables where you have uncorrelated random variables, and that's something that you do in 3610. You say random variable x plus random variable y, what's the variance? Which is like doing a power calculation. It's going to be the sum of the variances if they're not correlated with each other. So there's things that kind of come into play. That's what makes random signals so vital for communications and signal processing there. It's just behind that. This topic is no longer in the book, the generalized Fourier series, so I'm skipping over it. It's a cool topic, though. It just tells you that you can use a generalized Fourier series to expand anything. And I think most of you take linear algebra for one of your math electives, right? And so you talk about basis functions, and you get into abstract vector spaces where you talk about functions being coordinate vectors, as opposed to just thinking of the I, J, and K unit vectors that you first learn about in physics. So function spaces, and then being able to project a signal onto a function, and that is what Fourier series is really based in. We have a signal that we can decompose into its components as long as we are using an orthogonal basis function, and that's what the Fourier series expansion is. And this idea just says the basis functions could be pulses, if you wanted them to be, and then you can get the coefficients and so on. I think Dr. Ziemer took it out of the book because the editor said he had to have less pages. So in one of the later editions, he just had to go through looking to rip stuff out. Come into my office, you see I don't throw away too much stuff. I get more stuff piling up all the time. People give me stuff, and I need to throw away stuff.
It's going to be a fire hazard pretty soon.
Well, I'm not a hoarder, though, I don't think. I mean, that's a disorder, right? Have you ever heard of the hoarding disorder?
Oh, yeah. You used to beat my mom.
My wife and I do have problems, though, with throwing stuff away, and she's already told my sons that you're going to have to throw it away when I die. And my mother-in-law, who's still alive, lives up in Monument, she's already said that. And I've said to my wife, I said, can't we get your mom to sit down? Can't we start throwing some stuff out of her house? Because she's 87 right now. But for my father, who passed away a little bit less than 2 years ago, all of us siblings gathered when he had to move out his apartment and go into hospice care. We were there, we took our liberties, but then we let him come down and see a remaining pile of things that we just couldn't decide on. And he said, I want that, I don't care about that. A week later, he did pass away, but it's really hard. It's a really hard thing to do in life, I think. It's easy to say, I'm gonna let my children manage it, and all of you are gonna face that someday. My parents gonna leave it up to me and my siblings to throw stuff away, or are they gonna clean up? Both of my parents were pretty good about throwing stuff away all the way through. I'm not the greatest at it, but just something to think about.
Oh, man. Start stepping on enough Legos.
Dying.
Yeah, you'll start throwing stuff away.
Yeah. Okay, so the Fourier series that we're going to use in this class is the complex exponential Fourier series. And the basis functions are complex sinusoids, and they have integer n controlling the harmonics. So we have positive and negative complex exponentials. So the basis functions run from n going from minus infinity up to plus infinity. And the proof of the orthogonality between the basis functions is worked out right here. And also established in terms of the generalized Fourier series what the scale factor is, what the length squared of each of the basis functions is. It all reduces down to this relationship. We can synthesize a waveform from its Fourier series expansion, its coefficients, and its basis functions, and we can analyze a periodic signal x of t in terms of its Fourier coefficients x of n through this integral. The expansion is unique, so if you can get at this without having to do an integral and get the representation in terms of the synthesis of complex sinusoids, then you're good to go. And this little example from the book just says cosine squared. I use the trig identity, and I can just identify the Fourier coefficients from that immediately. The only little interesting twist in here is that here's a 2 omega naught and a minus 2 omega naught. Is the fundamental frequency omega naught, or is it 2 omega naught? This is just a little perplexing thing. Because there is no representation at omega naught for the cosine squared, it would probably be better to just say there is a DC component and then the fundamental is just at 2 omega naught. It's just a matter of preference, though. It's just the fact that when you square a signal, you get a DC component, and then you get a sinusoid that's at twice the frequency, and you don't have any fundamental left anymore. So you might just call 2 omega naught the new fundamental. I mean, it's purely arbitrary at that point. Does everybody see what I'm getting at, though? Now, in the homework problem that you're working, where you're identifying periodic signals that are sums of cosines, that's like a Fourier expansion. In there, we do want the fundamental. So if one sinusoid is at 10 hertz and the other one is at 1 hertz, the sum of those two sinusoids is a periodic signal, and the fundamental is 1 hertz, right? That's the greatest common divisor of 10 and 1. The greatest common divisor is 10 and 1 would be 1, so it would be 1 hertz. Throughout the entire semester, we'll be using this notation a lot, the time average operator, so it gets introduced right here. It's just something that has already popped up in calculating Fourier coefficients. It's actually been used to calculate the power, and it can be used to calculate the average value of a waveform. So the time average operator is the angle brackets, and it's just doing this integration from minus to plus infinity, dividing by the time interval, and then letting the time interval go off to infinity. So like I said, it can be used for the Fourier coefficients. It can be used for the power calculation, because if we have a periodic signal, then a special case of the time average is just integrating over one period and dividing by t naught. But if you wanted to get the power, then you could put in, v of t in a power calculation would be letting v of t equal the magnitude squared. So it's got a lot of uses, and we'll plug into it frequently because Dr. Ziemer liked to use it to simplify things in the book, and it just runs everywhere in the book at this point. So this is a convenient notation to get the Fourier coefficients, and then decompose them into the real parts and the imaginary parts if you want to. Okay, I think I'm about ready to jump over and give you some discussion out of Jupyter so that you can get some ideas on how you might do some things in the homework, or just get a workflow going. The next assignment will be having Fourier coefficient and Fourier series ideas in it, but that's then. So let's look in this notebook. Put it in the presentation mode so it gets a little bit bigger. So we see in the notebook how I've reiterated the definitions of rectangle and triangle, which weren't quite in the notes until I scribbled them in, but here they are again. And then I've just used the functions available in SIGSYS, which remember I'm importing up here. Also reminds me of another thing. I did put a link in here over to the document that I've been referring to, configuring Anaconda and virtual environments. I'd like to put more information in there, so I'm thinking about editing that and making it more universal rather than simply virtual environments. But right now, this is the other document I've been showing you, but I'm liable to update it some, based out on experiences with, who did I help get set up last Thursday? Successfully set up, right? It's not broken yet, right? So all we need to do is get everybody set up, and if you're already set up, you're good to go, but I'll help you with getting Python set up. At any rate, back over to here. So the rectangle and triangle pulses, I've just simply plugged into them here and created some pictures. So I have a time-shifted rectangle right here. I've just simply shifted the time axis. Or if I do Shift-Tab inside the parentheses, I'll get the help. And then I've given it a pulse width of 2. And here I've got the triangle shifted to the left by 2. And I'm giving it a half base width of 1.5. So the full base width of that should be now 3, right? Because tau is half of the width of the triangle. So if I look down in here, I see, yes, 3. And then I've got, wait a minute, something doesn't look right here. I've got 1.5, so yeah, it should be 3. But it doesn't look right to me, though. Let me do something that should be fairly simple. I'll just replace that with 0, and then it will center it. I'm confused because it doesn't look like it it is 3, yeah, it's 1.5. What am I talking about? Take that out of there. I did that to confuse myself and to confuse you. So make that be 1. Now it's going to run from -1 to +1. Because I wrote the software, my eyes look at something brand new again, and it's like, did I make a mistake? That many years ago? But in this example down here, when you run it, it uses the widgets. So if the widgets have been successfully installed, which takes some effort, which is on that web page I was just referring to, once you have the widgets going, though, then you can. And unfortunately, the widgets don't work with your finger, but once you get, that's the delay, so I can just see it shifting, or if I change the width of the triangle, I can put some interactivity in there if I want to. They work best with the mouse, though, and I didn't bring my mouse down here. So if you decide to go into this homework problem and look at it on the computer, what I already set up for you, I created a function. And right now, I just want you to utilize what I've given you. I want you to learn and study the code to see how I created the periodic function. But here, I created a function that creates and overlays multiple triangles. So it allows me to create the triangle signal, and we can envision it starting at -infinity to +infinity, just by the number of periods we overlay. And then I also plotted the absolute value squared of the triangle pulse. And the double asterisk is raising things to a power. In MATLAB, it was the caret, the hat, And in C, you have POW for POW, for power. Fortran, this is interesting. Fortran used the double asterisk for power. Why does Python use that? I don't know, because it's written in C, but maybe they think of asterisk as being a more standard symbol than the hat. Yeah, the caret. I don't know, but that's just something that gets going in your brain after a while. Actually, in C, the caret is XOR, isn't it? So I think that's what it is. In Python, it's going to XOR something if you do that. So they use something else. So let's just take and create a new notebook with a few minutes that are left, and I'll show you what. Well, I'll just take this whole notebook since I don't really have a choice with the time that I've got left. So I'm going to export this notebook, export it to Markdown. So it just saved it as a zip. I didn't run every cell in here, so I'm not going to have everything as well off as I was hoping, but I'm going to minimize my notebook, and then I'm going to go and look in my downloads folder. And so this is what I just created over here, and now I'm going to right click on that and extract all onto my desktop. And I went ahead and downloaded the Typora Markdown editor. And it expanded it. Lots of outputs are in here, lots of scalable vector graphics. But inside of here, there is one Markdown file. So if I double click on that, because I've already have Typora installed, it's going to open up the Typora editor for Markdown. And I can go ahead and freely edit things in here. It's got so much graphics in here now, and some of them haven't been fully rendered, so it's going to take a little bit of time to generate from top to bottom of this notebook. So actually I kind of did way more than I wanted to do. Try to slide back up to the top though. So like for example, I don't care about because that's exporting for LaTeX, so I can go ahead and delete that. I might decide to put a title up here though. I shouldn't have deleted that, so I can hold down Control and backslash or forward slash, and I can actually go in and type natively in Markdown if I want to. So I might put in title, and then a Control backslash will close that back up again. And then down below, title, I could actually put in
So you use Control backslash to get that?
Control forward slash.
Okay.
Yeah, you switch from compiled Markdown to the native syntax of the Markdown language, which is simplified HTML, which is the same Markdown language that you use in the Jupyter Notebook. When you type in a text cell or equations, you're typing Markdown.
See, I've never done this before.
Okay.
I just always import the Markdown files.
But you can hand tune it if you want to in here. It's kind of cool the way that works. You can also put in, let's see, table of contents. If you want to put a table of contents in, it's just generated one. So now you have hot links when you finally produce your document or your PDF. If you wanted to have that included, and then if you wanted to do like I'm talking about with the theme that I have loaded in here, I put themes in here, and I'm using this Misty theme Windows 2, and you learn about how to get themes put in from over here, where it talks about properties. Under properties, if it will open that up for me. You can see how you can add themes, where the folder is where you add themes. So, remember, and then you can also turn on things to put auto number equations and things of that sort too. I guess it's under general. So, somewhere in here, maybe it's not general, appearance. That's what it is. So we'll open up the themes folder, and you can drop the theme that I pointed out at the beginning of the course, beginning of lecture, into this folder, Misty Theme Windows 2. So at any rate, suppose I wanted to have a page break in here. When I render this out to PDF, I can go ahead and put in a horizontal line, and the horizontal line has got code I added to it so that this will put a page break in there. So if I go over to here and say export to PDF, it's going to spend a little bit of time because this was kind of a big document, but it's going to I'll put it on the desktop. Minimize this. I may have just thrown it away because I didn't answer some question properly. Yeah, it didn't get saved like I wanted it to. But at any rate, if we look at the PDF, it should have that page break in there. What did I? Oh, it's still processing it. That's what's going on. Exporting in process, because this is a very long notebook that had all those figures in it. Okay, so now it's done, and it's using the default web browser thing on this tablet, but it's opening up the PDF. So there it is. And notice there's a page break right after that table of contents. So and now you can print this anywhere because it's a PDF. And you can edit it, tweak it, and so on. And it came from the Jupyter Notebook. It's just one approach to get there for creating stuff. The other easier way, just cut and paste out of the notebook into a Word document and just print that page. That works pretty good too. A lot of different things you can do though. Everybody has a different style that they like to do for producing things. Well, I'm out of time. You know what the roadmap is right now to get to Thursday. So when you walk in here, have your calculator and your cheat sheet ready to go, and I'll hand the quiz out. We'll start a timer, and then we'll take up lecturing right after the quiz is collected, and you'll also have your homework papers up here. Probably before you sit down, just pile them up right here. Sound good? And I'm going to go back and stop my video.